Welcome to lecture 3, module 4. You will recall that in the last lecture, we looked into the Indian standard method of mix design. We will continue to look at that with an example now, and then we will start with British DOE method. So, our general outline of this lecture is IS method, example, and the British practice of Department of Environment DOE method, right. So, just to recall, the last when we discussed, we said that if you are using fly ash, in with cement, the IS method, IS 10262 method, when fly ash is used, it's suggested, it's recommended that you increase the cement plus C plus F should be, C dash plus F should be 1.1 C, where C is the cement content without fly ash, and if you are using fly ash, increase that cement content by 10%, and that must be the sum of the cement plus fly ash content. So, if you know F divided by C dash plus F, we have decided, let us say, to use this as 20% fly ash in the system. Then from these two equations, you can find out the fly ash and the cement content itself. Using these two equations, one is that increase the total by 10%, so 1.1 C. You have a control mix without the fly ash, which will have a cement content of C kg per meter cube. Now, if it is, let us say, is 320 was the C, then C dash plus F will be, let us say, something like 352 or so, somewhere close to this. You can approximately take that guideline. So, if you know F by C dash plus F, you can find out the value of C dash and F, where C dash is the new cement content and F is the fly ash content that you are using in the concrete. All right. So, this is just to recall what we were last discussing. We also said that we would need some correction factor for moisture content at the field, and in our example, we will look into these issues. So, right now we will look into an example using through IS method. So, the example is, we are assuming, we are choosing an M25 grade of concrete, we are assuming M25 grade of concrete, all right. Cement, we are using OPC, and assuming moderate exposure as per IS code is concerned, zone 3 sand, slump is 80 millimeter normal strength concrete and 20 millimeter MSA rounded aggregate, 20 millimeter MSA rounded aggregate, that is what we are using. So, IS method we will use to find this out. Now, you recall that in IS method, first step is to find out the mean strength, and target mean strength, as we call it, FM, is equals to FCK plus 1.65 sigma. That was the first step, if you remember, in IS method. And since we do not have any data available, let us say the starting point, we are taking standard deviation as 4 MPa, standard deviation as given in IS 456 2000 or in 10262. So, I have standard deviation as 4, sigma is 4, grade strength is 25 MPa, my target mean strength, if I calculate out based on this formula, then I get equals to 31.6. So, I choose a mean strength of 32 MPa and design the concrete. So, first step was to find out the mean strength, because as we said in the last class, that I can get an estimate of the mean strength through my cubes test results very easily with say samples, by testing samples. But FCK I can't get directly, then you need to test large number of samples, which is not very easy to do. So therefore, we design the concrete mix for target mean strength, and the mean strength is, we have found out, is 32 MPa. Then it says that you use the water content from experience, or if nothing is available, so either from experience, past experience if it is available, or from table 5 of IS 456-2000, from durability requirement. This is the table which gives the durability requirement. This table is IS 456-2000 durability requirement table, this is the table. And if you see the prescriptions, those are given for various exposure condition: mild, moderate, severe, very severe and extreme. The Indian Standard Code IS 456-2000 has actually classified the exposure environment into these 5 classes, namely mild, moderate, severe, very severe and extreme. And correspondingly, the prescribed minimum cement content and maximum water cement ratio and minimum grade of concrete are given in this table. This table is reproduced from IS 456-2000. Now, I also mentioned in our problem, earlier problem, if you look at it, our exposure condition was moderate exposure. Therefore, for moderate exposure, if I look at into this table, then the one which is colored blue, minimum cement content is 300, maximum water cement ratio is 0.5, and the minimum grade of concrete is 25. So we are doing design for M25. Therefore, these are the relevant one, M25, and this is the maximum water cement ratio permissible, and this is minimum cement content permissible. However, from experience, I take the water cement ratio as 0.45 deliberately, just as an example. Supposing I feel that 0.5 I may not be able to get 32 MPa mean strength, I put it as 0.45. So these are the two cases, either I take this or this. Now, since my experience says I shall be taking this, so water cement ratio star is 0.45. What I am saying is the water cement ratio I will be using is 0.45, whichever is smaller. So I am using 0.45. Then next is estimate water content from table 2 of 10262. So this table gives us the water content in kg per meter cube of concrete depending upon MSA. And I am using MSA 20 mm. So this is my thing. I should use a water content of this. So therefore, this is the line. So 20 mm MSA prescribed, as we have seen earlier in the beginning, and therefore my starting water content is 186. Now this is meant for the slump of 25 to 50 and crushed coarse aggregate. So I must apply some correction factor. These correction factors are this, because this table was for angular coarse aggregate and slump of 25 to 50. For each increase in slump of 50 millimeter or fraction thereof, I will increase the water content by 3%. So I increase 186 by multiplied by 1.03. My aggregate is rounded, so I subtract, because this is minus. For rounded aggregate, since they pack better, their packing is better, so they consume less water in the mix for the same workability. Right, paste content will be less, backing better, so therefore minus 25. So my water content therefore would be 186 into 1.03 minus 0.25 minus 25, which will give me 167. With a water to cement ratio of 0.45, so cement will be 167 divided by 0.45. Now, this will be my control mix if I am not using any superplasticizer or plasticizer. If I decide to use plasticizer, my water content will reduce. Let us say if I decide to use superplasticizer, I can reduce my water by 25%, which means my water will be simply 75% of this. So, basically you will have if I use a superplasticizer, at the moment in this example I am not considering superplasticizer, but if I intend to use superplasticizer, I can reduce it by 25% by using appropriate quantity of appropriate dosage of compatible superplasticizer. So, 0.75 of this will be 167 minus 4 2 or 41 less, you can say. So, this will be 5. So, about 125 or 126 liter per meter cube of water I can use. The cement also therefore will become 126 divided by 0.45, which will be something like, if you can see this 3.15 or 3 will be 42. So, this is 14 by 0.14 by, this would be 42 divided by 42, if I divide this by 9, so I get 0.05 and 14. So, 1400 divided by 5 is 280 kg. So, I could use 280 kg of cement if I was using superplasticizer and reducing down the water content by 25%, because my water would change from 167 to 0.75 into 167, right. Just let us see how it is. Okay, this is for our controller. Just let's look at it. Let's look at it first, the calculation part of it, then we'll come back again. So, first of all, what we are saying is that 167 was the water. Use superplasticizer. W will become 0.75 W, 0.75 into 0.75 into 167, and that was equals to 126, let us say, kg per meter cube. So, cement will be 126 divided by 0.45, which will be approximately equals to 280 kg per meter cube. So, you see you have a saving in cement as well. 280, water is less, cement is less. Anyway, that is why just I wanted to show that if you use superplasticizer, for the same workability you can save onto the cement, which we have seen earlier when we were talking about admixtures, right. So, which we have seen earlier when we were talking about admixtures. Now, in this particular case for the control mix, however, your water is 167, cement is 372 kg per meter cube. But if you use a superplasticizer, this will become 280, this will become 126 or something like that. So, anyway, this is how we do the select our water content. Now, we got our water content and we have also got our water cement ratio. We will come to this later on. Now, from the table 4, we can estimate the coarse aggregate volume in total volume of aggregate, and we said that our sand was zone 3. So, this is our zone 3 sand, we are using MSA 20, therefore, this will be this is not correct, 0.48 if I am using MSA 10, but if I am using 20 then it is 0.64. So, if I am using 0.20 it is still. If I want it to be pumpable, which is not there at the moment, then I can reduce it by 10%, but at the moment I have said it is 80 slump concrete only. So, there is no question of pumpability. So, in my case therefore, this would be 6.64 with MSA 20. So, MSA 10 it would have been 48, MSA 20 it is 0.64. So, my calculation should be done on the basis of 0.64. So, water to cement ratio is the minimum of these two, and is 0.45, minimum of these two and is 0.45. We found out water is 167 kg, cement is 167 divided by 0.45 or 300 from the durability requirement. So, maximum of these two, and this gives me 372 kg per meter cube. So, control concrete without plasticizer has got 372 kg of cement content and water cement ratio of 0.45. Now, based on this 372, I can find out, because we have chosen this as 0.64, right, and chosen this as 0.64 because for 20 mm zone 3 sand, we got aggregate is in the total aggregate, coarse aggregate is 64. So, fine aggregate will be 1 minus 0.64. So, fraction of fine aggregate will be, so the total aggregate, if I want to find out, divide the fine aggregate mass divided by its specific gravity and divide this by 1 minus 0.64, that must be equals to, so this is the volume of water, this divided by 1000, this divided by 3.15 and 1000 gives me the volume of cement. This gives me the volume of total aggregate, because this is the mass of fine aggregate, and fine aggregate occupies a volume of 1 minus 0.64. So, if I divide this by 1 minus 0.64, that will be the total volume of aggregate. So, fine aggregate divided by specific gravity gives me the volume of fine aggregate, divided by the, this term gives me the total volume of the total aggregate. So, fine aggregate quantity I can find out from this, and it comes out to be 695 kg per meter cube. Now, coarse aggregate I can calculate from the same formula, only thing it will be C coarse aggregate divided by 0.64, and specific gravity of coarse aggregate is 2.6. So, on that basis I get coarse aggregate is equals to 1190. So, my control mix without superplasticizer and without fly ash or anything, the mix without fly ash or plasticizer, I may not say this is a control mix. This will be a control mix if I am using a fly ash or using a superplasticizer. Then I have to find out, change this mix design for the superplasticizer and for the fly ash as well. We'll just do this calculation as well quickly, or at least show the steps. So, the water is 167, fine aggregate is 695 and coarse aggregate is 1190 kg per meter cube, right. Now, if I was using fly ash superplasticizer, then W will become, for superplasticizer, W will become 126, this will become 280, and correspondingly then this you can find out from this formula, 1 is equals to 126 plus 280 divided by 3.15 plus find FAGG divided by 1 minus 0.64 into 2.7. So, using this formula you can find out FAGG, fine aggregate content, this is unknown, and coarse aggregate correspondingly one can find out as 126, 1 is equals to 126 plus 280 divided by 3.15 plus coarse aggregate content divided by 2.6 into 0.64, and this equation you can use to find out coarse aggregate content. So, therefore, you will find that this value is higher, greater than this, it will increase now, and this will also increase, and correspondingly you can find out when you are using superplasticizer. If you are using fly ash, then let us see what will happen. If you use fly ash, say you decided to use 25% of fly ash, that is F divided by C plus F is equals to 0.25. This is what you have decided to use. So, your cement, new cement dash plus F will be equals to 1.1 into 372, which will mean another 38 increase, so it will become 400. Approximately it will become 400. And you have decided to use, let us say, 25%. So, that is F divided by C plus F is equals to 0.25. Let me erase this out again, do it like that. If I had decided to use F divided by C plus F is equals to 0.25, C dash plus F is equals to 0.25, which is equals to 400, so C plus F is equals to 400. So F divided by 400 is equals to 0.25. So F will be equals to 100. F will be equals to 100. The cement will be 300. So C dash will be 300. C dash will be, so F, new F will be, so if you are using fly ash, this can remain same, in fact it will reduce down, plus delta W, which IS code is not giving, but there will be some reduction. This will become 300 and fly ash will become 100. So you are getting a saving in cement, and correspondingly this also you can find out, but in the equation, the volume equation, you will have now fly ash divided by specific gravity of fly ash as well. So fine aggregate will also reduce, this will reduce somewhat, this will also reduce somewhat, because volume, fly ash will occupy more volume, cement will occupy less volume, but fly ash plus cement together will occupy more volume, because quantity is now 400, 10% increase. So 300 divided by 3.1, 3150 plus 100 divided by 2.2. So fly ash and cement will occupy more volume than the volume that was occupied by cement earlier, and now you will have therefore lesser fine aggregate, lesser coarse aggregate. I have not shown you these calculations with fly ash as far IS mix is concerned, but one can easily adopt this. The calculation I have not, I have just roughly tried to show you the calculation, not the complete calculation. Let me do it again, because our C was 372. So C dash plus F, C dash is the new fly ash cement content, will be 372 into 1.1, approximately 400, because 38 you will add to this and you get 400. Now F by C dash plus F I said is 0.25. Therefore F must be equals to 0.25 into 400, which makes it equals to 100. So volume occupied by fly ash will be this divided by, so this is fly ash as this. So cement volume will be now volume cement, so therefore this is F is 100. So now my new situation becomes C dash is equals to 300, F is equals to 100, W is equals to 167, which might reduce a little bit. So I will set an equation like this: 1 is equals to 167 plus 300 divided by 3.15 plus F divided by F is 100, and specific gravity let us say is 2.2. So 100 divided by 2.2 by fine aggregate divided by 2.7 into 0.36, and whole of these things should be divided by 1000, and I will find out the fine aggregate content from this, and it will be less than 695. It will be less than 695. And if I put in coarse aggregate here, divide this by 0.64, I will find out coarse aggregate content, which will also be less now. Total aggregate will be less now. Total aggregate content will be less, and fine. So therefore, you see there is a, if you use fly ash, it is just not replacing. It is not just not replacing the fly ash by some of the cement by fly ash. You are not doing that actually. Fly ash addition will reduce down the sand requirement or fine aggregate requirement as well as the coarse aggregate requirement. Also it will reduce down. The cement requirement, even if we keep the water content same. But if the fly ash is good, it can reduce down the, it has got sufficient fines in the system, sphericity, spherical particle. It can in fact reduce down the water requirement also and save on further cement. So If you use together fly ash and compatible superplasticizer, you can reduce down the cement content even more. So 300 if you use fly ash alone, 280 if you use a superplasticizer, but it would be much less, let's say 25% less than the amount that you are using, you know. So 126 liters with the fly ash, 126 liters with the fly ash, the water cement ratio is, you know, you can actually reduce down still more the cement content, and that's of course anyway right now, I mean, one can understood from whatever our discussion has been. So this is how, up to this we determine the mix design, mix proportions, and let us see how we do the total is 2425 kg per meter cube. So in 1 meter cube the yield will be 2425 kg per meter cube if I sum up all these masses, but while transporting and mixing, you know, after mixing while transporting, in fact some of our water evaporates, you will get it somewhat less. There is some loss both due to reaction, autogeneous, you know, desiccation, auto desiccation and evaporation, then this mass will become somewhat less. So otherwise this should be the mass of the concrete at the fresh state. If you have now site correction would be, there will be some site correction, because water content at the site would be less, water content of the aggregate will be somewhat less, I mean somewhat more. So there has to be some correction at the site. So if the measured water content is known, if the, you know, if you remember, if the, let us say water content of aggregate is WAGG, SSD absorption is WSSD, right. So excess water would be, you know, this, let us say for the coarse aggregate, fine aggregate let us say is negligible water absorption, and there is no water at the site as well. If there, you have to subtract this. So this is WAGG minus, if this is greater, if it is, if you know, like if it is greater, so WAGG minus WSSD is the moisture content per unit dry mass per unit SSD mass. So this is the additional water, right, additional water, and this additional water multiplied by the CAGG mass of the aggregate, coarse aggregate mass, this must be added to the water content. This quantity of water is additional water, this must be added, and correspondingly you must add aggregate as well, because aggregate contains additional moisture. If it is less moisture, then you might add some water, slightly more water should be added, because a good lot of it will be absorbed to bring it to the SSD condition, and the aggregate quantity that you are adding, that should be less than the actual measured aggregate quantity, because in SSD condition mass will be higher. So accordingly one might do this correction. So that's all about the mixed design method as per IS code is concerned, as per IS 10262 is concerned. So with this now we can look into DOE method. We can look into the DOE method, and DOE method starting point is same, step 1 is same. Of course the next step is, I am calling this not as a step 1, but step 1 then is selection of water cement ratio from curves. Step 2 is then estimate water content based on slump, BB time, etc., MSA and shape of aggregate from a table. So this is what we do, you know, this is a slightly different table. And step 3 is calculate cement content, which you can do because you know the water cement ratio and you know the water content. So step 3 you can do. Step 4 would be wet density of concrete, that's again from a set of curves, and total aggregate content you can determine then. Step 5 is determination of fine aggregate based on MSA, water to cement ratio, and grading zone of sand from a set of curves. So, let me just repeat this. First is target mean strength, same as IS code. Next, you select water cement ratio from a set of curves. How you do it, we will come back to this. Then you determine the water content from a table depending upon the slump or VB, that is workability factor, and depending upon MSA, maximum size of aggregate, and whether it is a rounded or crushed aggregate based on that. So, you determine water content, you have determined the cement content. Now, next step is to determine the aggregate content. That is done from a set of curves which gives wet density of concrete versus water content. Since you know the water content and specific gravity of the aggregate, you can find out the wet density. So, if you know the wet density, subtract the volume of cement from that, or mass of cement from that, mass of water from that, you get the total mass of aggregate. Proportion of coarse to fine can be obtained from again a set of curves where it gives you the proportions of fines depending upon water cement ratio, grading zone, etc., etc. So, these are the step 5, and then site corrections are all required. So, this is the step 5 steps which I mentioned. So, first target mean strength I am not discussing anymore because we have already talked about it when we were talking of IS method. We will look into water cement ratio determination. This is the kind of curve where you plot free water cement ratio. Free water cement ratio means the water that is available for free water, water that is available for reaction, that is after SSD condition, after absorption to SSD condition. So, this is free water cement ratio against compressive strength at 28 days, 8 days let us say. So, this is a strength versus compressive strength versus water cement ratio relationship. Say 28 days compressive strength you can find out, but now there are infinite number of curves here. So, you should select a curve. How do you select? You start at water cement ratio 0.5, and DOE method gives you a very large table where for various types of cement and aggregate type, the possible strength at 0.5 water cement ratio are given. So, for example, OPC and SRC, sulfate resisting cement, if you have crushed aggregate, you might assume it to be 40 MPa. For uncrushed aggregate, you might assume the strength to be 47 MPa, right, for same water cement ratio 47 MPa, because this is largely because crushed aggregate packing related issues. So, it gives you 47. However, such thing will be valid for only UK condition. This may not be valid in Indian scenario. So, if you are or any other scenario. So, if you want to start, you need not rely on this table. Same method you can use because it is also based on cube strength, and same thing FCK plus 1.65 sigma same. So, use this same concepts which you use in IS code, but you cast a trial mix with 0.5 water cement ratio with your cement, with your aggregate, etc. A trial mix you cast with 0.5 water cement ratio. So, starting point will be at 0.5 water cement ratio. Now, supposing you have done that and obtained a strength of, let us say 25 or so, somewhere like this 25 strength you got. So, 25 or so, and now with 0.5 water cement ratio you got 25, therefore, you can select your curve. With 0.5 water cement ratio, if you would have got 30, a curve would have been this, but right now you have got this, therefore, your curve would be something like this. This is the curve, this is the curve. So, because you have got 25 MPa, so correspondingly you can select the curve. You can always skip the lower curve if you have got somewhere in between. So, make it a conservative, little bit conservative. So, this is how you select your curve, strength versus water cement ratio curve. Now, supposing your target mean strength is 32 or 40, target mean strength is 30, then the water cement ratio would be, or 32, same as before. The water cement ratio would be in this curve, draw a line at 32 and this will be your water cement ratio close to 0.45, close to 0.45. It is same as the example that I have taken, actually deliberately taken that way. So, therefore, you can find out your water cement ratio in this manner. Let me repeat. First you cast a trial mix, first you cast a trial mix, first you cast a trial mix with 0.5 water cement ratio. Determine the 28-day strength. You can even accelerated test you can do, but this is to be done only once, for your system. Later on you may not do. For any grade of concrete this is done. With the same results you can use it for any grade of concrete. For example, M25, M30, M40, you can design it for any grade of concrete. So, you have got, let us say, with 0.5 water cement ratio, the strength somewhere here, which is about 25, but you want to get around 32 strength. So, this helps you in identifying the curve. So, a trial test at 0.5 water cement ratio helps you identifying the curve which you should be using. Otherwise, there are too many curves, you do not know which curve to be used. So, you find out which curve you want to use and then find out which curve you want to use, then go to your target mean strength, draw a horizontal line up to that curve. So, this was my curve and up to this point, and this I project downward to get the water cement ratio. So, which I got around 0.45. So, water cement ratio can be determined in this manner. So, the next step is to determine the water content. Well, these curves can be also put into equation form. That is what we have done actually, because these are hyperbolic curves and you can fit it in this form. A K1 plus K2 to the power W by C is something similar to Abraham's law, which says A by B to the power water W by C. So, K2 is nothing but B to the power minus 1, Abraham's constant, So, this one can fit into this curve, and if one fits into this curve, it has been observed that K1 can be related to log of 0.5 strength. So, each curve, there were so many curves, for each curve, if you know the 0.5 strength, you can find out K1, and similarly K2 you can find out. This has been done, a regression analysis we have done, and we have found out that K1 can be related to log of 0.5 strength for f0.5, and K2 can also be related like this. So, if you know 0.5 strength, you can actually find out K1 and K2, and therefore, you can know for any other water cement ratio what is the strength. This is doing it in an equation form, because instead of using the chart, this becomes very useful if you are doing it in Microsoft Excel or any other spreadsheet. Next step would be to determine the water content. Next step would be to determine the water content. And water content determination is based on a table. I have actually I have reproduced the part of the table, it gives you slump, also BB time. I have not written the BB time, part of the table I said slump. So, for various MSA 10 mm, 20 mm, 40 mm, for uncrushed and crushed aggregate, it gives you the water content for various slumps. For example, in our case it was 80 mm slump, we would have used possibly 195 kg per meter cube of water, 195 kg per meter cube of water, which IS code gave us 167. If you go through that example, here we would have used 195 kg for uncrushed aggregate. This is rounded aggregate, but if it is crushed, then this would be more, right. So, 40 mm this is less, and so on and so forth. So, one can find out the water content from this table, no correction required. Then calculate the cement content. Now, cement content will be minimum of water cement ratio from the curve, water cement ratio should be minimum of water cement ratio from the curve and water cement ratio from durability. So, again if this was 0.45, this is 0.5, I will choose 0.45 only. if you have coarse aggregate and fine aggregate, one of them is crushed, other is not crushed. One of coarse aggregate is crushed and fine aggregates are not crushed, let us say, natural. Then you take 2/3 water for fine aggregate, 1/3 for coarse aggregate. So, for example, this is, let us say, is 195, this is 225. So, just go back to this table, you go to back to this table, this is 195, for crushed it is 225. So, if my coarse aggregate is crushed and fine aggregate is uncrushed, then the water content of the mix will be, the water content of the mix will be 2/3 of the fine aggregate. So, 2/3 of 195 and 1/3 of that for coarse aggregate. So, that is how I go about it, and therefore, 2/3 2 by 3 195 plus 2 to 1/3 225, which will work out to be 130 plus 75. So, which will make it 205 kg per meter cube. So, it will be 205 kg per meter cube if courses, but it will depend upon what type of aggregates you have. So, water cement ratio would in our case would come now actually 0.45 if you go from that figure, and cement content will be maximum of water content divided by water cement ratio star, which is 0.45, and in this case this was 225 or 195, and C from durability, which is 300 kg. So, whichever is higher you take that. Next step would be to determine the aggregate content. Now, we know the cement content, we know the water content, we got to determine the aggregate content. This is done from a figure like this, where free water content is plotted, the wet density of concrete is plotted against free water content for various specific gravities of aggregate, So, you know specific gravities of your combined aggregate, specific gravity you can find out because you know the combined grading, their proportions and all that, and you know your free water cement ratio. Let us say if it is 195, it will be somewhere here, and if you know the type of aggregate or aggregate specific gravity, then you can take this as, let us say, 2450 or something like this. So, you can find out the wet density. So, you know the wet density of concrete in kg per meter cube. You know the mass of the cement in 1 meter cube, mass of the water in the same 1 meter cube. Therefore, rest of it must be the aggregates. So, this is the principle that is applied, right. So, for example, mine was 190 or 195 and this was my specific gravity, let us say, then this will be my water content to wet density will be somewhere around 2450. Just for an example, supposing this is 190, this is 180, 190, and this is the crushed aggregate and so on and so forth, and you are getting 2450. Calculate the total aggregate content would be the next step. Continue with the step 4. Total aggregate content is due wet density, mass of the aggregate, total aggregate is equals to wet density minus C minus W, where C is the cement content, W is the water content, right. So, we know cement content because we know the water cement ratio and we know the water content. In this particular case I was telling you, it would be 195 divided by 0.45 is a C and water is 195. So, this would be 66 and 0.15. So, this would be 22 divided by 0.05. So 22 divided by 0.05 is 2200 divided by 5, which will be 450. No, 440. So 440 will be the amount of cement you require in this particular case, because 195 divided by 0.45. But if you use plasticizer, you can reduce this 195 by 25%, the cement consumption will also go down. So that's how we find out. Now the last step in this DOE method is determination of fine aggregate based on, so you have curves like this, determination of fine aggregate, you have set of curves like this. You can see there are 4 curves. This is for slump 10 to 0 to 10 mm, this is for 10 to 30, 30 to 60 and 60 to 180, and this curve is for 20 millimeter aggregate. X-axis is free water cement ratio, y-axis is proportion of fine aggregate in total aggregate by mass, proportion of fine aggregate in total aggregate by mass. So if I know my wet density was 2450, let us say 2450, water was 195 just for the sake of understanding, and cement was 440. So the aggregate content will be sum total of these two, which is 5, 635. So 2450 minus 635 is 15. 1835 would have been the aggregate content, total aggregate content. Now out of which how much is the fine aggregate content? That will depend upon the proportions of fine aggregate by mass in total aggregate. So this is proportion by mass, and this depends upon what is my slump. Supposing my slump is 6 to 180 and 20 mm aggregate I am using, and my water cement ratio is 0.45 or something, and I have got a zone 3 sand, so somewhere, or zone 3 or zone 2 sand somewhere here. So therefore I know it's about 30%, let us say, by weight. So out of 30%, just let us say 30%, so this will be 544, you can find out 30% of this, right. So 540, somewhere around 545 kg would be the fine aggregate, depending upon which zone does it belong to, etc., etc. In fact, which range does it belong to, and which range does it belong to, which range does it belong to, and this is given here. For example, the zone 1 is for percentage passing through the 600 micron sieve, 15%. So if it is percentage passing through the 600 micron sieve, that is grading of the fine sand is such that percentage 600 micron, percentage 600 micron sieve is 15%, 2 is 40%, 3 is 60%, and 5 is 100%. Now, if it is passing through the 600 micron, that is the quantity of real fine in the system, or it is grading. The zone 5, that is the range that is shown as 5, the curve number 5, sorry, the curve number 5, this is curve 1, curve 2, curve 3, curve 4, curve 5. So curve 5 corresponds to a very fine sand, whereas curve 1 corresponds to relatively coarser sand. Only 15% is below 600 micron, the rest all is above 600 micron. So therefore fine content increases as we have coarse material in the system, because that then coarse aggregate will reduce, fine content will increase. When fine is very fine, then you have got maximum amount of fine to use, and this also depends upon the slump. For a higher slump, you need more fines, lesser coarse aggregate. This is understandable, because as I told you, coarse aggregate don't contribute to moldability, right. It is the paste and then the mortar and their flowability contribute to the workability. So therefore this is step 5, and this is meant for 20 mm. Similar curves are available for 10 mm and 40 mm MSA as well. This is for 20 mm MSA. So by doing this, then you have found out the complete proportion of fine coarse, because you know the proportion mass of actually W fine aggregate FAGG divided by total aggregate WFAGG plus WCAGG, both sum total is in the left vertical axis. Therefore total aggregate content you have found out by subtracting the cement content and water content from wet density. Wet density you have found out from the curve, and then once you have found out the total aggregate content, proportions of the fine in the total is known. If the sand is finer and you need higher slump, you will put more sand, right? And it will also depend upon the MSA. Higher the MSA, you will require less sand, because packing of the coarse aggregate will become better. And then it also depends upon water cement ratio, because cement contributes to the fine as well. Cement contributes to the fine as well. So higher water to cement ratio means, higher water to cement ratio means you will be using more cement as well. So depending upon that situation, fine materials, it will depend upon that. So all put together, this curve gives you the quantity of fines. Curves are available for 10 mm and 40 mm as well. So you calculate the fine aggregate content as fine aggregate content is equals to Pw, which you have obtained from the previous curve, multiplied by WAGG, where WAGG is the total aggregate content and Pw is determined from the previous curve. So CAGG is equals to WAGG minus fine aggregate content. So you have found out the total proportion of material in the concrete without fly ash and without superplasticizer. If you are using fly ash, then this is the method available. If you are using superplasticizer, then reduce down the water content, and rest all will work in the same manner as you have done it for IS method. If you use fly ash, first you prepare that calculate for the control mix, and then calculate the proportions for the fly ash mix. So total percentage of pulverized fuel ash, fly ash is a pulverized fuel ash, or maybe just a fuel ash, may not have pulverized this. So is fixed as specified or desired. So how much fly ash you would be using, that has to be fixed by yourself, like we did even in IS system as well. So this is known to us, and water content would be reduced, because fly ash acts like a, or fuel ash acts like a kind of, it gives you better packing. Therefore, as we have discussed, this we have discussed in module 3, when we are talking of supplementary cementitious material, this fly ash would reduce down your water requirement, because it's spherical and the fine fly ash does this job very well, and this method actually allows for reduction in water content. So delta W is the water reduction, new water content will be W dash. So this water content reduction is given in a table, and part of the table is here actually. So depending upon the fly ash content percentage in the total material, and also the slump range, the delta W, the water content reduction, delta W, is given here. For example, if you have 20 mm MSA, you have slump of 60 to 180, and if you are using pulverized fuel ash, then you can reduce the water content by 15. So if it was 195, you can make it 180, and so on and so forth. So you can reduce it down. So your water gets reduced if you are using fly ash. What happens to the cement? How do you modify the cement? It suggests that you modify the cement content in this manner. First, you find P is given by C divided by C dash plus F into 100. So F can be written from this, because F can be expressed in terms of P, and F will be written as P by 100, right. So F divided by C dash plus F is given by P by 100. So F is equals to C dash plus F into 100, P by 100, and you want to separate out F. So you will get F equals to 1 minus P divided by 100, 1 minus P divided by 100, okay, 1 minus P divided by 100 is equals to C dash into P by 100. So F can be found out, which is given in this equation. That means C dash divided by P, right, and this can be written as 100 minus 100 divided by 100. So 100 will cancel out. So you will get this expression for F in terms of P. You will get expression for F in terms of P. You will get expression of F in terms of P, and WC dash star is, you put, this is for the control, and you write that's equivalent to an equivalent water content, where you use a factor called K factor, which gives us the amount of reduction, which gives us the a factor which is less than 1, and gives us the equivalent cement of fly ash. For example, if K is 0.3, 100 kg of fly ash is equivalent to 30 kg of cement, 0.3 into 100. So, if fly ash multiplied by this is equivalent cement, so this is equivalent water cement ratio. Therefore, C dash can be obtained from this equation, because W by C star is known, P is known. So, combining these two equations, you can get C dash from this equation, which you can calculate out, because this is equals to just F is equals to P C dash by 100 and P. So, replace F here and you will get this equation, 100 minus P into W dash divided by 100 minus 0.7 P into W by C star, where K is taken as 0.3. So, take K as 0.3, C dash equation will be this. K3 is a conservative value, but as a first approximation it says that take K as 0.3. In fact, in practical situations in India, some cases it is the observation that K could be as close as 0.6, 0.7 even. Some places of course it could be lower. So, K 0.3 is quite conservative, and that is why IS code did not adopt this kind of a principle. Instead, it decided to take about 10% increase in the total cementitious. So, that is how we find out. For durability, find out the water to cement ratio that is allowed, and in that case no K is used, right. So, this, but only thing is it says that maximum P, the P that you can use would be as per the criteria of IS 1489 part 1, which is the IS 1481 allows for maximum fly ash, limits the maximum fly ash that can be used in Portland pozzolana cement. So, P should not cross this limit if you are using it in this formula, and this is true for IS method as well. So, maximum water to C plus F instead of maximum water content. This we will discuss again when we talk of durability. So, this is from durability criteria, and C plus F wet density is assumed same as control mix, follow the same procedure, only fly ash will be now reduced, and fine aggregate content is calculated as before. So, using DOE method you can also obtain a mixed design using fly ash, as I told you. Procedure is by and large same, 5 get the control mix, and then you get the fly ash content, etc., etc. Only thing is it uses a K factor now, IS code does not use K factor, and K, suggested K is around 0.3. So, to summarize, we have now looked into an example of IS code, we have looked into DOE method, and in this DOE method we have also looked into mixed design with PFA, that is pulverized fuel ash or fly ash, etc., etc. So, with this we conclude the module 4 lecture 3. Thank you very much.